Okay, guys, welcome. Today we're going to talk about exponential functions. Now, we say that a function is an exponential form if it has this form, right? It's a number raised to a power with that power specifically being the variable, right? So you have a to the x. Now, of course, we need some restrictions. We need a to be positive. We also need a to not be 1, right? Because if a is negative, then you have negative numbers to sort of odd and even powers appearing sometimes, which can sort of get messy, right? Because then you're going to have flipping back and forth. Now, if you have a equal to 1, then you just have 1 to the x power, which of course is always going to be 1, which is a straight line, right? So we require these two things for a. Now, of course, we call a the base, just like we would before, and the variable x, we can plug in any real value, so there's no domain restrictions. And of course, the variable is in our exponent. All right, so let's take a look at what the graph of one of these things might look like, right? So let's just sort of do it with a table of values, sort of assuming that we don't have any tricks. Right, so since I can plug in any x value, let's do our usual -2, -1, 0, 1, and 2. Let's try and make that line straight. All right, that's a little better. Okay, so something like this. Okay, so for example, if we plug in -2, we're going to get 2 to the -2, right? Well, by our negative exponent rules, this is 1 over 2 squared, which is 1/4, right? If we plug in -1, we get 2 to the -1, which is 1 over 2 to the first, which is just 1/2. If we plug in a 0, we get 2 to the 0, and anything to the 0 power is 1. If we plug in 1, we get 2 to the first, which is 2. And if we plug in 2, we get 2 squared, which is 4. Right? So it looks like we get -2 comma 1 over 4. We get -1 comma 1/2, 0 comma 1, 1 comma 2, and 2 comma 4 as our points. Right? So if we plot these points rather, so it's -2 comma 1/4 will give us something like this. -1 comma 1/2 will put us up here. 0 comma 1 will put us here. 1 comma 2 will bring us up to here. And then 2 comma 4 will bring us up to here. So it looks like we're going to get something like this. Right, and of course we're just going to hug the axis here, right? We're never going to cross over or even get to 0, right? And of course, how do we know that we're not going to get to 0? Because just imagine that you make those numbers more and more negative, right? So -100 or -1,000 or something. Now, if you plug that in, you're going to get 2 to the -100 or 2 to the -1,000, which will then become 1 over 2 to the 100 or 2 to the 1,000. Now, that's going to make your number in the bottom of that fraction extremely large, but still positive, right? So you're going to get 1 over a big number, right? And of course, 1 over a big number is a small number, right? Because if you think about it, take 1/2, that's 0.5. Take 1/4, you're making that number bigger, you're making it 0.25. So as you make that number on the bottom bigger, you're going to make the number overall smaller, right? And that's exactly what's going to happen as you sort of move to the left on this graph. All right, so let's look at another one. Let's look at the graph of 1/2 to the x, which you could also think of as 2 to the -x. Both of these are sort of equivalent. All right, so let's go ahead and let's do our table of values again. And let's draw our graph. Okay, so let's see what we got. Now, if we plug in a -2, we're going to get a 2 to the -2, right? Which is 2 to the 2, which is just 4, right? And again, we're allowed to make this consideration because we can think of 2 as 2 over 1, right? And if you have 1 over 2 to the x, right, you could just as easily make that exponent negative and flip that fraction, right? So then we have a 2 to the -1 for the next one, and we'll get 2 to the first, which is 2. Then, of course, 2 to the -0 is still 2 to the 0, which is still 1. But then we get 2 to the -1, which is 1 over 2, and 2 to the -2, which is 1 over 4. Right? So we're sort of getting the mirror image here of the previous problem, right? So -2 comma 4 put us up here. -1 comma 2 will put me here. And we have 0, 1, 1, 1/2, and 1, 1/4. Right? So this is going to be exactly the mirror image. So we get something like this. Of course, that should go through there, but I can't draw very well. So something like that. All right, so we're getting the mirror image. And again, keep in mind that this will not cross over, but it will just sort of hug the axis. All right, so let's talk about some properties of exponential functions, right? Now, one thing that you're always going to get is you're always going to get the point 0, 1, regardless of what your a is, right? So you're going to have 0, 1 will always be a point because if you plug in 0, anything to the 0 power is 1, right? So that's always going to happen, right? Now, the next property that we'll have is that you're basically going to have two general shapes, right, for your exponential functions, right? You're either going to have this shape or you're going to have this shape, right? And sort of what's going to dictate what shape that you have is what that a value is. If a is bigger than 1, like in the first example that we had, your general shape is going to be like this, and it's going to be an increasing function. Now, if your a is between 0 and 1, because remember, a can't be 1 and it can't be negative or even 0, it's going to look like this. And of course, be a decreasing function. Right? And those are the sort of the two general shapes that your exponential graph can take on. Right? Now, of course, the domain of any exponential function is the set of all real numbers. And we saw that the range, all your possible y values, is only the positive numbers, right? You couldn't get a negative to come out, and we also couldn't get 0 to come out, right? So your range, the numbers that you can get to as y values, would only be the positive numbers, right? So this next property that we have says that if x is positive, then raising a number to a positive power sort of works in order, right? If I raise a smaller number, right, let me put it this way. So if we have a less than b, and I raise both sides to the x power, this is sort of preserved, right, that direction of that sign, right? But if x is negative, right, if I have a less than b, as soon as I raise x to a negative power, or sorry, a and b to a negative power, then that inequality sign flips, right? So just be careful with that. And then our last two properties that we have, let me give myself a little bit more room, are going to be important because they say that if we have a to some power equals a to another power, that really means that those powers have to be equal, right? And then another property that we have is that if we have a to the u and b to the u, as long as u is not 0, then this is going to imply that a would have to equal b, right? So those are going to be key here sort of in the next couple problems. Okay, so for example, in part A, we have 3 to the 10 is equal to 3 to the 5x, right? Well, if we have 3 to a power equals 3 to another power, we know from before, from the previous slide, that this would imply that 10 has to equal 5x. Those exponents really have to be equal, right? So then if we divide both sides by 5, we get that x is equal to 2, right? In part B, we have that 2 to the 7th is equal to x minus 1 to the 7th. Now, since both of those exponents are equal, that means that these two things have to be equal. So that means that 2 is equal to x minus 1. So once we add 1, we're going to get that x is equal to 3. Okay. Now, part C is interesting because we have 3 to the 3x is equal to 9 to the x minus 1, right? Now, with this type of exponential equation, we don't have the bases are equal, right? 3 and 9 are not equal. And we don't have that the exponents are equal either, right? So we have to be a little bit more creative, right? But luckily, we can write 9 as 3 to a power. So we can write this as 3 to the 3x is equal to 9, which I'm going to think of as 3 squared to the x minus 1, right? So I'm just replacing this 9 with 3 squared, right? Which, and of course, they're still the same. But now if I apply my power to a power rule, this right side is going to become 3 to the 2 parenthesis x minus 1. So now I have 3 to the 3x is equal to 3 to the 2 times x minus 1. So that means that these two exponents have to be equal, right? So then we have that 3x is equal to 2x minus 2 once we distribute. So once I subtract 2x from both sides, I'm going to get x is equal to negative 2. Right? So if you have an exponential equation in which neither the base nor the exponent is equal, you want to rewrite both sides with the same base first, and then you can apply those properties. Okay. Now, the next thing that we need to talk about is the number e, right? And you are hearing me correctly. I am saying the number e, right? So there is an irrational number that plays an important role in math, and we denote it by the letter e, right? So now we usually approximate this number by saying it's around 2.71828. But like I said before, it's a rational number and it continues forever. So it's sort of like pi in that sense, right? So you have that this number e is approximately equal to 2.71828, right? Now, sort of the way that this comes about will be something that I'll mention on a little bit later in this video to sort of give a more precise definition of where it comes from. But for now, this is really what we need to know, that e is just some number and this is about what it equals. Now, we can use this number e to model exponential growth, right? So if we have this equation here where we have q of t is equal to q0, right, where q0 is some initial quantity, and then t represents time, and k is some growth rate. Right, so let's go ahead and let's look at an example of that. So for example, we have that the number of bacteria in a culture after t hours is described by the exponential growth model, 50 times e to the 0.17. Now for part A, we want to find Q0, find the initial number of bacteria. Now there's really two ways you could do this. You could just look at the equation and say, well, this is an exponential growth equation, so whatever number's out front is my Q0, right? And that's one way you could do it. Now the other way that you can sort of see it is make t 0, right? Because that's the initial time. And then you get 50 times e to the 0.7 times 0. Well, then that exponent is going to become 0, and e to the 0 is just 1, so you are going to get 50 that way as well. All right, so either way, you're going to get that the initial bacteria Q0 is 50. Now in part B, we want to know how much is in there after 10 hours. Well, 10 hours represents time. So we're going to have t is equal to 10, right? Because t is our time. So we just want to find q of 10. So if I'm finding q of 10, I need to do 50 times e to the 0.7 times 10, which is 50 times e to the 7th, right? Now, if you're going to use this form, and again, this is something that you have to use your calculator for, make sure that you put this entire exponent in parentheses, all right? But if we use our calculator, we'll find that 50 times e to the 0.7 times 10, or 50 times e to the 7th, is going to be approximately equal to 54,831.66. Right, so this is a fast-growing culture of bacteria. All right, because after 10 hours, we went from 50 to 54,000, almost 55,000 actually. Now, for exponential decay, we essentially have the same model, except now your exponent is negative, right? That's all. So the nice thing that you can easily tell is that if you have e to the positive number times t, that represents growth. And if you have e to the negative number times t, that's decay. Right, and of course, again, k is usually given as a percentage. So we'll have that, for example, if your growth rate is 3%, then your k is 0.03. All right, so that's what we sort of mean here. So we're told that a substance has a decay rate of 5% per hour. We're also told that if 500 grams is present initially, how much will remain after 4 hours? Well, if we're given a decay rate, that's like a k. And if it's negative, it's a negative 0.05 once we convert it to a decimal. Now, 500 grams is initially present, so that's my Q0. So Q0 is 500. And we want to know how much of the substance is left after 4 hours, so that's T is equal to 4. So again, the exponential decay model looks something like Q0 e to the minus kt. So in this case, my Q0 is 500. Now I already made my k negative because I knew it was decay, so this is negative 0.05 times t, which is times 4. So again, this is one that we'll do in the calculator, and if you're going to put this in the calculator, make sure that that decimal, that exponent is on parentheses. So if we enter this in, we're going to get about 409.37. And that's how much would remain after 4 hours. All right, so that's some examples of exponential growth and decay. Now, one interesting application of exponential growth is the idea of compound interest, right? So of course, compound interest is different from simple interest because any interest that you accumulate also starts to go towards your interest, right? Whereas if you have simple interest, you're only gaining interest on the initial deposit. Any interest gain is not helping you, right? But in compound interest, it is, right? So just to write this a little bit more clearly, this formula is given by A is equal to P times 1 plus, and then we have R over N to the N times T, right? So A is your final amount, P is your initial amount, and then R, of course, is your rate of interest as a decimal, N is your number of compounds per year, and T is the number of years. So let's go ahead and we'll jump into an example. So we're supposing that $6,000 is invested as an annual interest rate of 8% compounded quarterly. And we want to know what will the value of the investment be in 3 years, right? Since we're compounding quarterly, that means that we're looking at a compound interest problem. So now we want to fill out as much as we can and then solve for what we don't have, right? Well, 6,000 is invested, so that's P. Then we have an annual interest rate of 8%, so that's R is 0.08, and it's compounded quarterly. So if it's compounded quarterly, that means it's 4 times per year, so N is 4. And then, of course, we want to know what's the value of the investment after 3 years. So that's T is equal to 3. So now it looks like we're solving for A, and we just need to plug this stuff in. So we're going to get A is equal to 6,000 times 1 plus 0.08 over 4 to the 4 times 3. Right? So I usually just like to go right to the calculator and just plug everything in rather than try and simplify it. You just need to make sure that you're careful with your parentheses. So let's do it. I want to do 6,000 times 1 plus 0.08 divided by 4, and then I'm raising that to the 4 times 3. So we're going to get that A is roughly equal to 7609.45. And of course, we're talking dollars and cents, so we'll always round these to 2 decimal places. Right? So the value of the investment after 3 years will be about $7,609.45. Okay. Now, I mentioned that we'll be able to show where we are going to end up with sort of a definition of E, right? Now, the idea here that we're going to talk about next is continuous compounds, right? And that's basically taking your number of compounds per year, and we're going to do this an infinite number of times, right? And we're going to get continuous compound interest, which is A is equal to P times E to the RT, right? Now, essentially, this is giving us the definition of E, because if we have the number E, you can show that this is 1 plus 1 over 1 over N raised to the N, and you're basically just making N as large as possible. Right. So this, I'm not going to go into too much of the details, but that looks similar to what we have in the compound interest formula, with just a couple of extra terms added in there. And that's essentially where this is coming out, right? But let's go ahead and we'll do an example of that. So here, we're supposing that $20,000 is invested. So again, this is compounded continuously, so this is A is equal to P times E to the RT. And since $20,000 is invested, that's like our p-value. Now the annual interest rate, 7% per year, so that's R equals 0.07. And we want to know what's the value of the investment after 4 years, so that's T equals 4. So then we're going to get that A is equal to P, which is 20,000, times E to the R, 0.07, times T, which is 4. So now if we plug this into the calculator, we have 20,000 times E to the 0.07 times 4. And again, make sure that that exponent is all in parentheses, and we'll get that A is roughly equal to 26,462.60. Right, so that's continuous compound interest, right? So the formula becomes a little bit easier, actually, because we're allowed to replace that sort of that complicated expression with E. Okay, now I believe this is the last problem. Yeah, so we want to suppose here that we're investing amount P, right? So here we don't know P, and it's continuous compound, so it's A is equal to P E to the RT, and we have an interest rate of 8%, so 0.8, and we want A to come out to be 10,000, and T is 5 years. So we want to know how much should be invested now. So once we fill everything in, we're going to get 10,000 is equal to P times E to the 0.08 times T, which is 5. So now to get P by itself, we need to divide by this E term. So 0.08 times 5. So we're going to get that P is equal to 10,000 divided by this E to the 0.08 times 5. And if we let our calculator do that, we want to do 10,000 divided by E to the 0.08 times 5. And that's going to tell us that we should invest $6,703.20 if we want to end up with this $10,000 in 5 years. All right. So those are some applications of exponential functions. So that wraps up this video. I hope you enjoyed, and I will see you next time.